Hi, welcome to the Olympiad geometry. Let's continue our study on the triangle incenters. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe the channel. Thank you. As we introduced in last video, we said we will talk about this figure more. So let's see it. In triangle ABC, AB is not equal to AC. AD is perpendicular with BC. D is altitude foot on BC. O1, O2 are incenters of right triangle ABD and right triangle ACD, respectively. Line O1, O2 intersects AB on K and AC on L. If AL equals to AK, prove that angle BAC equals to 90 degrees, right? Proves the triangle BAC is a right triangle. So this problem is actually very difficult. I would encourage you to try to solve it and try to think about the ways that you can use. But eventually you will find that the point B and point C are kind of symmetrical, and also the O1, O2. So basically, the conclusions that we can derive from the problem set constrain us on either triangle ABD or triangle ACD. And that's a problem because we're trying to prove that angle BAC equals to 90 degrees, which means that we need to find a way that connects the triangle BAD and the triangle ACD. So here I show one solution, and that's the only solution I can think of. If you know, or if you can derive other solutions, please contact me and send it to me. I would like to show that to others as well. So first, let's look at this figure, right? As I said, if you try to work on this problem for some time, you can find that it's difficult because just because all the conclusion that we can get is constrained either on triangle ABD or on triangle ACD, which means that we need to find a way to break it, right? And that's the only thing we can find. So the triangle ABD and triangle ACD has a common edge AD. So if we don't use this edge AD, we can never connect the triangle ABD and triangle ACD together, which means that we need to find a way to use this AD. Okay, and we know that AK equals to AL. AK is in triangle ABD, and AL is in triangle ACD. Right, so look at KL. It passed through O1, which is the incenter of triangle ABD. It also passed through O2, which is the incenter of the triangle ACD. It reminds us one property. Let me just write it here, that in a triangle ABC, if there is a line passing through the incenter of the triangle ABC and intersect AB on P, intersect AC on Q, we know that AB to AP times sine angle B plus AQ to AC to AQ times sine angle C equals to sine angle A plus sine angle B plus sine angle C. right? We proved this before in the Incenter property video. Let's just use this, okay? So for the triangle ABD, let's call this point as M, and line KL, right? We can use this. So here, triangle ABD and line KL, which is KM here, it passing through the incenter O1, right? So we have AD to AM times sine angle BDA or ADB plus AB to AK times sine angle ABD, right? It equals to sine angle ABD plus sine angle BAD plus sine angle ADB, right? And also to the triangle ACD and line KL, we have AC to AL, right? AC to AL times sine, oh, actually, let me just start from this side. So that's AD to AM, right? AD to AM times the sine angle ADC plus AC to AL times the sine angle ACD equals to sine angle ACD plus sine angle ADC plus sine angle DAC, right? So if we set this angle BAD to be alpha and angle DAC to be beta, right? We can rewrite this equation to be these two equations to be AD to AM times sine angle ADB, that's 1, right? So directly plus AB to AK times sine angle ABD, which is cosine alpha. Cosine alpha equals to sine angle ABD, that's cosine alpha plus 1 plus sine alpha, right? Similarly, for the next equation would be AD to AM plus AC to AL times cosine sine angle ACD, that's cosine beta, equals to cosine beta plus 1 plus cosine alpha, right? We already know that AD, see here, AD to AM, that's a common term in both equations, and AB to AK, here is AC to AL. We know that AK equals to AL, right? So we can just use AB to AK. So from these two, we got AB to AK times cosine alpha. Cosine alpha is AD to AB, right? AD to AB plus AD to AM equals to cosine alpha plus 1 plus sine alpha, right? And for here is AC to AL times cosine beta. Cosine beta is AD to AC. So AD to AC plus AD to AM equals to cosine beta plus 1 plus sine beta, right? And see here, AB can cancel, right? AC can cancel. So we got AD to AK plus AD to AM equals to cosine alpha plus 1 plus sine alpha. And also AD to AL plus AD to AM equals to cosine beta plus 1 plus sine beta, right? That means, see here, because AK equals to AL, so AD to AK equals to AD to AL, and AD to AM is a common term, so the left side would be equal, so we got cosine alpha plus sine alpha equals to cosine beta plus sine beta. Right, if you're familiar with this, it's already tell you that alpha either equals to beta or alpha plus beta equals to 90 degrees. But we can expand this a little bit based on this figure and then to prove it. So what is cosine alpha? Cosine alpha is AD to AB, right? And sine alpha is BD to AB. It equals to cosine beta. Cosine beta, that is AD to AC. And plus sine beta. Sine beta is DC to AC. Which we got that AD plus BD divided by AB. Right, what is AB? AB is AD squared plus BD squared. And it equals to AD plus DC 2 squared AC squared plus AC squared AD squared plus DC squared AD squared plus DC squared, right? So we get AD plus BD squared divided by AD squared plus BD squared equals to AD plus DC squared divided by AD squared plus DC squared, right? So we got AD BD to AD squared plus BD squared equals to AD DC to AD squared plus DC squared, right? And from this, we got BD to AD squared plus BD squared equals to DC to AD squared plus DC squared. So we have BD times DC squared minus BD squared times DC plus BD times AD squared minus DC times AD squared equals to 0, which means BD minus DC times AD squared minus here BD times DC BD minus DC equals to 0. So we got BD minus DC times AD squared minus BD minus DC times AD squared minus BD times DC equals to 0, right? We already know that AB is not equal to AC and AD is perpendicular with BC, right? So if AB equals to AC, then BD equals to DC. But AB is not equal to AC, so BD is not equal to DC, which means this term is not 0, which means AD squared equals to BD times DC, right? So we get AD to BD equals to DC to AD. And we already know that angle ADB is 90 degrees, angle ADC is 90 degrees. So we got triangle ABD is similar to triangle CAD, right? Which means these two triangles are similar, so the angle ABD equals to beta, and angle ABD plus alpha equals to 90 degrees, so alpha plus beta equals to 90 degrees, right? So this problem is not an easy one. It's kind of difficult if you want to just prove it through the angle rather than this kind of algebra solution. I think this is a very interesting problem. It uses properties that we discussed before. Okay, and it just finished the discussion about this classic figure, right? I hope you like this video. See you in next one. Thank you.